Welcome everyone, and thank you for joining us this evening here on Zoom. We will begin shortly. We're waiting for more attendees to join us. Thank you. Thank you for joining us this evening and welcome here on Zoom. We will begin shortly. We are awaiting more attendees. Thank you for your patience. Thank you for joining us this evening and welcome to the Unplugged 360 series. We are awaiting more attendees and we will begin shortly. Thank you. All right, thank you everyone for joining us this evening and welcome to the Unplugged 360 series. This evening we have Dr. Nathan Meehan, who's going to speak about our role in the energy transition. Now, before I hand over to him, I'm going to go over some house rules. Second, points of order. You will not be able to use your microphone or be seen by video on the webinar. We will hold a live Q&A session at the end. So please submit your questions here on Zoom. And for those watching on the YouTube channel, please do so as well. We will get to your questions as well. We have Nathan here answering questions for 20 to 30 minutes this evening. It's a little bit longer than usual because I'm sure it's going to be a fantastic talk. So without further delay, I will hand over to Dr. Nathan Meehan. Thank you.
Great. Thank you. Well, I'll go ahead and share my slides. Okay, are we seeing those?
Yeah.
You see my, okay, great.
Yeah.
Thank you. Thank you very much. I appreciate this. I only wish I could be there in person. My wife and I have traveled throughout Scotland, and of course, enjoyed Aberdeen. My kids, I will tell you, their preference is Edinburgh. Um, but I have been to Aberdeen many times and have enjoyed it and been very impressed with the section there. You have an outstanding group who are heavily engaged, and I miss it. My wife misses tablet in the morning, which is something we don't have here. Anyway, I want to talk a little bit about what petroleum engineers in specific, what their role can be in the energy transition. I'll talk a little bit about the need for that. And first, sort of acknowledging my shortcomings. There's a quote here that I sort of live by. You know, if anybody tells you, speaks ill of you, don't make excuses. Just say they were ignorant of your other faults. Otherwise, they would not have just mentioned those. So I'll have a number of faults and shortcomings, but you just don't know me well enough if you only know those. Fossil fuels have gotten a bad rap lately, and our business has been challenged. I would submit that this is about as bad a time in the oil industry as any time we had in the 1980s, which were pretty seriously bad. And profitability has dropped. Our bankruptcies are as high as ever. Want to set that in context. Last year, I wrote an article called "The End of Petroleum Engineering as We Know It," and it was the most downloaded article of the year. In that article, I argued that petroleum engineering in the future would have to be different. That we might have fewer petroleum engineers. But that those engineers would be far more engaged in digital work than in the past. As well, they would be much more involved in the decarbonization efforts. That if we were going to continue as a profession, that carbon capture and storage would going to have to be a vital part of what we do. So I have these graphs for every part of the world. These come from the Baker Hughes data set. This is the oil, gas, and total rig count just for the United States since the mid-'80s. And what you can see is that during that long period of low activity in the 1980s, which I've previously referred to as not a cycle, but an ice age, drilling activity in total less than between 500 and 1,000 rigs. All those were, I'd say 90% of those would have been vertical wells at the time. Then we had a big change go about as natural gas prices really began to increase during the early 2000s. The United States started building natural gas liquids import terminals, or at least planning for them. Almost all of those eventually became export terminals. The unconventional activity really started out in the early 2000s, but by 2006 and 7, the natural gas drilling activity was really high, and the supply was just going through the roof. Oil prices also spiked up briefly to $140 a barrel, and then came crashing down in early 2000, in the 2008, 2009 time period. That was just, and then increased again, and we saw the oil activity grow up as we hit $100 oil in the 2012, 13, 14 range. Activity around the world jumped up, and as prices plummeted in conjunction with global oversupply, we really thought we'd seen the worst of it. But we got this V-shaped recovery as you can see in 2016 time period, we hit this bottom and then just jumped right back up. Well, starting about December of this year, of last year, we started seeing inventories climbing up again everywhere. That coupled with a disagreement between the two largest members of the OPEC Plus group on production cuts, then accelerated by the COVID retraction in demand, North American rig count has absolutely collapsed. The Baker Hughes rig counts are rotary rigs. Now, I'm going to guess that few, if any, of the listeners here have ever been on the type of drilling rig that preceded rotary rigs. That's our cable tool rigs. And if you don't know what that is, I'll leave it as a Google exercise for the listener. But I've been on a cable tool rig. It was at the museum in Midland, admittedly, but cable tool rigs were what the first oil wells were drilled in the United States with, and that was in the early 1860s. And by 1865, there were 500 or 600 cable tool rigs active, and we never really got fewer than that until after World War II. If you combine cable tool activity with rotary rig activity, the current rig count is the lowest that has been since Abraham Lincoln was president in about 1864. So that gives you an idea just how low this activity level is. And one of the drivers for that activity level being low is inventory. This is an inventory by day, if you will, on the x-axis, 0 to 365, each curve representing a year. This is total crude oil and petroleum products. You can see the same answer with crude oil. And if you go back and look at what happened in 2016 and why those prices collapsed and went to the very bottom, you can see that the inventories reached a higher level than it had been almost forever. Now I have 2005 and I skip ahead to 2015, but if you look at 1995 to 2014, they're just all curves noisily scattered around that lower green curve. It's just seasonal variations, and the variations from year to year were not high. But we started seeing significant growth in inventory, both in the US and worldwide. In 2016, we just had this huge peak in inventory. And that continued almost throughout the whole year. But by 2017, we saw that inventory starting to fall off in the second half of the year. And that's what led to the recovery, both in terms of prices and activities. And so earlier this year, when our inventory levels were at a seasonal location at about day 124, it looks like on this graph, it was not obvious to me whether we would go like we did in 2016, in which case I would have expected that we would not have had price improvements, or 2017, where I would have expected price improvements. But in fact, of course, we've gone much worse than 2016. International inventories are not quite this bad when you look at those numbers, but they're still really quite bad. So until we are on a longer term basis consuming more than we produce, inventory numbers are not going to come down. And a real recovery is not going to happen in terms of prices until the inventories reach a little more normal level and the anticipation is there. Right now, we're still producing more than we consume globally. We're actually adding to inventories on the planet. So we're, the question is, are we riding a storm out? My apologies to the band. Or are we in an ice age? You don't ride out ice ages. You've got to change in the case of an ice age. And so we don't know whether the world's crude oil production peaked in January of 2020. We don't know when coal peaked, to be honest with you. A lot of people thought it was a few years ago. It may very well be that the peak coal is ahead of us, and that oil might peak before coal does. But there's little question that going forward, everybody anticipates coal use to diminish. Various forecasts show relatively flat demand for oil. The demand for oil as a transportation fuel is generally flat to decreasing over the next few decades, over the time period of your professional careers, which I assume will extend well past 2040. Almost all forecasts have some growth in natural gas demand, but the absolute growth in energy demand is expected to be taken up by renewables, principally wind and solar. That's the big ones. We'll see some biofuel growth, very little expected demand for hydro, and varying different interests and forecasts on demand for nuclear. One thing though, every time we forecast demand for renewables, we have underestimated it just every time. So on the left is a graph. If you look at the bottom curve, that's the World Energy Outlook 2006 forecast of gigawatts of solar capacity installed from 2005 to 2030. That original curve on the bottom. And then you see a dash curve just above it for the 2008 forecast, and so on for 2012 and 15. The red dots are the actuals. The green dots are the 2017 forecasts. I have no doubt that we will exceed the forecasts that we made in 2017. Similarly, on the right is the wind capacity. And you can see that the magnitudes are order of magnitude similar in terms of, but the estimates have been revised upward very dramatically. In the case of solar, 15-fold increases in forecasts and a 3-fold increase in forecast wind capacity. So we've underestimated renewable growth every single time. And so at one point, oil and gas companies were forecasting that renewables would continue to be only a small sliver of the total. Now the forecasts are that essentially all the growth in energy demand is going to come from renewables. No one is forecasting that oil and natural gas combined in aggregate in terms of BTUs is going to be anything substantially different than roughly flat between now and 2040. One of the reasons, of course, is the climate change issue. And I'm going to go through some of the issues associated with that. First, there is overwhelming scientific evidence that we need to decarbonize the energy system. Now, I've got a picture here of high temperatures. That's not the evidence. That's not scientific evidence. That's a weather phenomenon. And we've had really hot summers in the US and Europe on and off over many decades. And so the observational evidence I'm talking about is not the fact that it, got really hot, or it might be hot this summer. I think it's pretty pleasant today in Aberdeen. It's about 100 degrees F here in Houston. But guess what? It's always hot in Houston in the middle of the summer. And so these record-smashing heat waves that happened in Europe over the last, within the last 20 years, and certainly within the last 5 years, while they motivated a lot of people to get out and protest, these aren't the evidence that I'm going to be talking really about. If you go look at all the sort of scientific evidence and observations, and I'm not going to go into them in a great deal of detail. In 1972, I traveled up to Canada with my brothers in search of glaciers. And we went starting at Glacier National Park and up into Alberta and British Columbia. And we saw with our own eyes that glaciers had been retreating, and obviously retreating for quite a few years. And so you can see that the mass changes here as a function of time had preceded us in that time period. And there are only a few years where there were additions to the global mass changes. And in this part of Canada, we could have old timers there that would say, yeah, when I was a kid, the glacier came all the way down to here, and now it's gone up here. That has accelerated in terms of mass change losses since my brothers and I were up in Calgary last. And so the rate of glacier retreat and mass losses in glaciers is fairly well mapped around the planet. And there's little doubt that it's been accelerating, relatively speaking, in the 20th century. The amount of CO2 in the atmosphere is now about 440 parts per million, or 420 parts per million, sorry, up very significant from the pre-industrial period. And that correlates very closely, of course, with CO2 emissions over time. And so the CO2 emissions that happen, they're those in excess of what are used by the planet, captured by plants and other things, either goes into the ocean or goes into the atmosphere. And so what we've seen is this very significant increase of CO2 emissions tied to increasing CO2 concentrations in the atmosphere. Now, I'm going to assume that the listener is familiar with the concept of greenhouse gases and what the drivers are there. I've written up quite a bit in this area. The most important greenhouse gas, of course, is water vapor. And the greenhouse gases get their name essentially from real greenhouses. Now, in a real greenhouse, it's a little house that mainly has glass roof and typically walls, allows sunlight to come in, and it eliminates convective airflow so that it maintains higher temperatures internally. Now, that's different than what this greenhouse gas emissions are. But almost all molecules with 3 atoms or more, and a few with 2 atoms, have the ability to capture some radiant energy and reflect it back to Earth. And that the specific wavelengths associated with that, how long they do that, how long they stay in the atmosphere, dictate how significant these greenhouse gases are. And without, the water vapor and the greenhouse gas effect, we would, Earth would be a big ice ball. And so it's very important to life. That said, it can have excessive amounts and heat the planet excessively. So these CO2 emissions over time have varied by country. Now, unfortunately, the scale on this one does not show you just how dramatic the US reductions, which are the blue curve, that they look roughly flat. But from the peak in the mid-2007 time period to today, there's been a very substantial decrease in CO2 emissions, slightly larger than the total decrease in the EU. And that has been driven almost exclusively by increased use of natural gas displacing coal. But beginning in roughly 2000, you see the dramatic increase in CO2 emissions from China. During the time period where you see this sharp increase, China was adding 1 coal-fired power plant per week, a little over 50 a year. Now, the data shown on this graph say that they have miraculously stopped CO2 growth. There's some debate about how accurate the last few years' data are. Because China continues to build coal-fired power plants, not so many. The biggest and most rapidly growing contributor today, though, is India, where significant power growth fired by coal is occurring. And planetary CO2 emissions, although some places like the US and the EU are declining, planetary CO2 emissions are continuing essentially unabated, more or less on the continuing trend that they've been on. And so these concentrations of CO2 continue to rise, and with it go the temperatures of the planet. Now, it doesn't make much sense to talk about what the average temperature of the planet. I don't even know what you would mean there. So what people do is we compare in the various measurement sites around the world, and these have been tracked for quite a while, what that temperature is compared to a baseline time period. Now, in this particular graph, that baseline time period is entire 1881 to 1910 period. So that becomes the baseline, that becomes zero. So what is the anomaly compared to that? So those temperatures, the anomaly, should roughly average zero under the 1881 to 1910 period. And what you can see is really beginning in about 1960, we started seeing the increased temperature anomalies across the planet. There were some anomalous ones in before or after that, but you probably could write those off as statistical noise. If you look at that and compare it for land and ocean, the land data is got a sharper increase. And again, that entire time period from 1880 to 1960, by the way, the zero base here is all of 1900 to 2000. It's a slightly different source for what that temperature anomaly is. Essentially, if you just looked at the data with no lines through it from about 1880 to 1970, you might not see temperature increases. But if you look past that, it's very hard to interpret it as anything other than significant temperature increases, both in land and on the ocean. Other observations, I'll just go through them quickly. Most of the snow on the planet is in the northern hemisphere, almost really the vast majority of it. Antarctica doesn't have that much snow. Got lots of ice. But if you look at the aerial extent of how much of the planet is covered with snow, you can do that by season. And you can see there is a clear decline. And of course, there's a feedback loop on here because very clean snow, very white, fresh, snow has a high reflects a lot of the energy back to it. It's the albedo. So it reflects a lot of solar energy back. The darker land mass that's exposed absorbs more of that heat. And so there becomes sort of an accelerating effect here. Global sea levels, obviously, this varies based on where you are. And you have to look at the sea level observations. This is mainly done, the recent data is from satellite sea level observations. And there's sea level observations have been made for a long, long time. But because those aren't from satellites, it's very difficult to see consistent information. And there's some confusion associated with near shore subsidence. Some areas are subsiding more than others. A few areas in the earth are uplifting. And so the sea level changes are complicated by that, whereas the satellites give you much clearer information. So we're seeing sea level rise. The rate is just over a centimeter a year. That level is forecast in almost everyone's model to accelerate somewhat as we go forward. So in addition to this overwhelming scientific evidence and observational evidence, the global engagement levels are enormous. And for us, it's not so much protests in the street, our uncles not wanting to talk to us because we work in the oil industry. The reality is investment community, banks and PE funds, everyone else, they're steering clear of oil and gas investments and insisting that we clean up our act to warrant further investments. So we really can't ignore the changing political environment. Now, the United States, we have a current system where we're probably, at least through next January, there's not going to be any serious laws that will change it. But this is not the case across most of the world. The reason that this enormous change in the amount of solar and wind has happened is because the rest of the world has decided they want to support alternative forms of energy. Most of the energy investments that are going and happening now in terms of dollars are happening for renewables. The planet has invested more than $3 trillion of public money in support of these investments. So there's a lot going on here, but again, we're going to be a vital part of this solution. If you look at what the world looks like just a few decades from now, we are going to have closer to 9 billion people than the 7.2 billion that we have today. They're all going to need electricity. They're all going to need energy. They're going to need much more than they have now. How do we protect the planet? How do we provide clean, safe, affordable energy? And the problem, of course, with some of the renewables is that it's not as reliable as oil and gas, and it's not necessarily as affordable as oil and gas. So how do we make that happen? How are we there? And so part of that has become because in conjunction with extraordinary results offshore Brazil and in deep waters around the world, the unconventionals have added an enormous additional resource of oil and gas, in particular natural gas. So the natural gas and natural gas liquids can provide a thermal fuel that is accessible. And now, because of advances LNG, because of advances in floating regas and some other technologies, we're able to distribute gas globally as a commodity like we've been able to do for oil for a long time. So the places like California and parts of Europe that really are emphasizing driving decarbonization, natural gas is going to be vital for that transition. And we have to play our role if we want to achieve anything like the CO2 reductions, whether it's the Paris Accords or any other goal. Now, these global shale basins, if you look at where those shales are, they're pretty much throughout the world. The biggest activity, of course, is in the US and Canada, followed by China and Argentina. But there are opportunities, and I guess Australia as well. There are opportunities a lot of places, and they will require some better prices. But in addition to this, if you map on the tight gas resources, we have an enormous supply of natural gas that's going to be affordable and doesn't really require too many more advances in technology to exploit almost all of them. So if this is on the left, an example of some of the growth in natural gas production, it's just been amazing to see how rapidly this has happened. Natural gas production shot up. The scale of this graph is a little more compressed, and so shows the CO2 emission reductions in a little more startling way for the US, and shows how they compare and correlate just with those increases in natural gas production. So one thing we know is that fuel switching works. And you saw that global long-term tail on coal use. Almost all the forecasts still have us using a lot of coal throughout the 21st century. Accelerating natural gas production and replacing that coal is the #1 thing that we could do to lower planetary CO2 emissions. That's more than anything else. That individual technology is well established. Now, we really need this additional thermal fuels. I've got graphs like this for many different factors. this one's gross national income per capita, but it applies equally well to access to electricity, literacy, infant mortality, child mortality, educational opportunities. Every measure of quality of life correlates with annual energy capacity, energy use per capita. So you see a dramatic relationship with quality of life. So we've got 7 billion people now. We're going to have 9 billion people by 2050. And all of those people want to move up and to the right in this curve. They want to improve the standard of living. They want to improve their GDP per capita and infant mortality numbers. And every one of them will use more electricity and energy in that process. Now, I hope that there's something we could do to improve the slope of this curve so that it doesn't require people in India who want to have the lifestyle of people in Canada to have a 20-fold per capita increase in energy. And if that's the case, we're going to have a very serious problem to supply that much energy for the world. We can probably make most of that progress with more efficiently if we can. Other factors in why we need thermal fuels. The World Health Organization identified air pollution as the #1 source of avoidable deaths. And 70% of those were due to indoor air pollution. And millions and millions of people die due to cooking indoors with wood, animal, and crop waste. More children die because of pneumonia associated with cooking with these fuels than die due to malaria, dysentery, tuberculosis, and AIDS combined. So air pollution globally contributes to 1 in 8 deaths. So I know the coronavirus is serious, but this is an enormous source of avoidable deaths. And this process of having poor people out searching for wood and gathering animal waste to cook and heat with, the burden of that falls disproportionately on women. And the impact is disproportionately on children. And so there's having safe, affordable energy is one of the best things that you can do to improve quality of life in the world. Now, we tend to take it for granted, but in reality, throughout much of Africa and to a lesser extent Asia and China in particular, people are still doing this. There have been some pretty significant advances in China, but in total, the number of people without clean burning fuels has remained roughly constant in the last 20 years. Okay, so you can see that's that number by area. So the sub-Saharan Africa and India have grown in terms of the people without clean cooking access, whereas China has been improved somewhat. So we contribute substantially to quality of life for the planet. So again, I mentioned this before. I didn't show you this over time. This forecast is from the 2018 BP Energy Outlook. Today's most recently released one has a much flatter energy outlook for oil and shows a slight decline. Natural gas continues to grow. It hasn't changed all that much, except again, the renewables have a slightly higher set of numbers. Everybody has very similar numbers to these. And in order to minimize those greenhouse gas emissions, we're going to have to do several things as a planet. Obviously, growing our reliance on renewables is one of them. Another one is increased efficiency in energy consumption. So those two are great big. And just as big as those are carbon capture and storage. We need to take carbon out of the atmosphere and out of the environment. And that scale is very dramatic. If you look at the carbon capture required to meet Paris, we're talking about a curve here that is really dramatic. both power industry and other use of CO2, this is how much we need to take out of the atmosphere. Currently, there are projects that take out about 30 megatons of CO2 per year. That's our current carbon capture and storage, 30. And by 2035, you're looking at needing not 10 times that, but 100 times that, 3,000 megatons or 3 gigatons. That is roughly equivalent to the volume that's produced global oil production. And by 2050, the 2050 time period, we're looking at something that's going to take twice the global oil production volume. The amount of money required to do this, just to achieve that first goal, is roughly the amount of money that it corresponds to the entire investment of the oil and gas industry, the entire capital that we've invested. So we've got to rebuild and generate essentially an entire additional industry to achieve these goals, if we're going to achieve these goals. And no one is better suited for identifying the places to store CO2 underground, for capturing, handling, transporting that CO2, monitoring those reservoirs to make sure the CO2 stays where it's supposed to, than petroleum engineers. We have a bright future in this industry. We're going to also have to dramatically reduce methane production and emissions that occur associated with production. Every time we go measure these, it's surprising how much higher they are than reality, than we expected. So for a sustainable development theory, we're having to look at substantial reductions in methane emissions. Right now, they account for 6% of global greenhouse gas emissions. Methane is a much more powerful greenhouse gas in terms of its impact on climate change. And so the numbers we're going to need are dramatic reductions. And those are all really quite possible. This graph, this planet view here is from some work at Stanford in a public tool called OpG that measures the carbon intensity of production from the wells to the refinery. If you wanted to get the total impact of carbon intensity, you'd have to add the refinery to wheels. That actually doesn't vary as much for barrels of oil as you might expect. The number of carbon atoms in a barrel of oil are roughly the same no matter what kind of oil it is, and how it's used and how efficient the refineries are, that varies. But the variability in terms of from the wells to the refinery is really quite startling. So the color codes are the carbon intensity. And so that's sort of grams of CO2 equivalent per megajoule. You could think of it as, pounds of CO2 per barrel that are emitted associated with producing and transporting the oil. And you can see that Saudi Arabia has very attractive numbers over in the right scale. They have relatively few wells per barrel. They don't have high water handling costs. They don't have a bunch of flaring, all the way up to Venezuela, which has very heavy oils, a lot of thermal, a lot of issues. Canada is a red color, both because of SAG-D and thermal, but also because it needs some hydrocarbon diluents to transport some of the heavy oil. Some of the countries are in here because of serious flaring problems. The numbers associated with the countries are not the carbon intensity, but they're the absolute magnitudes. So Russia, while it has a relatively low carbon intensity because of its huge production, has a very large total magnitude of carbon emissions. These are the components of those carbon emissions. The OpG tool actually has over 50 variables that are included in there. But if you look at the various contributions, the red one is venting, flaring, and fugitives. It's the largest single contributor there. And it's really the thing that we need to focus on and reduce most rapidly. I don't know how many of you got to see me on video, maybe by the time we do this, but there's a great big flare going off behind my head in my Zoom background. So 3 weeks ago, I was out in West Texas, and this is an image of one of the hundreds, if not thousands of flares I saw that day driving around West Texas. It's a very substantial problem, and it's the #1 source of greenhouse gas emissions associated with oil and gas production, on the wells to refinery side. Obviously, the use of the crude oil is the #1 total absolute use in terms of greenhouse gases. So if we look at flaring, this is a little outdated, but the numbers haven't really changed that much. The total amount of flaring is embarrassing numbers. They're very high. The carbon intensity numbers change a little bit. The flaring intensity, SCF per barrel, Russia doesn't look so bad in this one, in that particular case. But we have got opportunities to reduce flaring. Flaring should be infrequent, brief, and efficient. And one of the things, as we observe, well, here you can see that little video of that flare out in West Texas. One thing, when we go and make measurements on these flares, we find out that not nearly all of the methane is being burned in that flare. A lot of methane goes through that flare. They're inefficient. Now, in a refinery or petrochemical plant that has steam that it can inject in the bottom of the flare, they can get efficiencies that are up in the high 90s if they're very careful. The kinds of flares we see otherwise can be below 50%, but it routinely 60, 70% numbers. And we're seeing a lot of carbon dioxide, of course, emissions as we burn methane, but straight methane going to the atmosphere. So people are monitoring methane emissions generally associated with production, with pipelines and leaks. So on the left, you see drones. There are ground-based things. There are satellite-based technologies. Every time we go and measure methane emissions, they outstrip what we estimated them to be. You'd be surprised how many are just an open tank battery. So the good news, if you want good news, is our total impact that we could make, both in the oil and gas industry and the rest of the industries. If we can just lower our CO2 emissions 4% per year, we have a decent chance of staying below the 2 degrees rise above pre-industrial levels. So that the bars, the line here is cumulative CO2 emissions on the planet. The dots are more or less where we are today. And if you wanted to plot those dots and update them to 2020, they're still on the same black line. And so if you continue unabated, we're looking at blowing through the 3 degrees per sea level. Now, in the next 20, 30, 40 years, a lot of the developed world, even if we went ahead and went through this 2 degree level, a lot of the world would see modest changes. Some of the world would see very dramatic, radical changes. But if we stay at 3, the whole world sees very dramatic, radical changes. And that's going to be some horrific things that we need to avoid. So we need to be engaged in lowering this. I'm going to take one quick story and then we'll open up for questions. When I was a student at Stanford, I had a professor who had previously taught at Harvard, and a friend of his had a beautiful home on a lake, owned the whole area around the lake. It was covered with beautiful trees, but there were weeds growing up through the lakes. And now this is not his actual place, but I took this photograph in Western Massachusetts, and I talked to the lady who lived in this house, and she told me that when she was a child, she was quite old at the time, but when she was a child, this was a lake. And then in the course of her lifetime, these weeds had grown up and overtaken it. And in another 50 plus years, this is going to become a bog and will disappear. And a lot of lakes that were associated, you can see them on early maps of Massachusetts. There used to be a lake here and it's gone. So my friend, my professor's friend hired a lake expert. I'm not sure how you get those. They're called limnologists. And he told him that he needed to put 1.5 feet or half a meter for the rest of you, of sand all over the bottom of the lake. He hired a couple of companies to give him bids. They came up with bizarre, extremely expensive ways to accomplish this. They were going to have to knock down the barn trees and build these pulleys and drop sand. And it was very elaborate. It was going to cost close to $1 million. And he didn't want to spend that much money on his lake, but he didn't want to lose his lake either. And eventually someone came to him with an idea for a lot less money. And that idea was basically to wait until late January when the lake froze over, put 1.5 feet of sand on top of the lake, and then wait till spring and summer, which is of course what they did. And to my mind, this is why I'm so excited about the next generation of petroleum engineers. This is the group that are going to help us solve problems by looking at them differently. You're going to figure out a way to put the sand on top of the ice. All right. So I will go ahead and stop sharing my screen here, and I think we're having time for questions.
Okay. Thank you, Dr. Nathan Meehan, for that very informative talk. We'll if you have questions, please type them into the Zoom. Now I don't believe we have any so far, so I've prepared some throughout the course of the presentation. So I'll go ahead and ask the first one, Nathan. So if world demand is going up, that's assumption one, and the percentage of world oil demand is constant based on the stacked bar chart you'd shown earlier, and on the basis that kind of quote unquote easy oil's already been found. And the third assumption is that there's a diversion of capital away from the oil industry. Does that not mean that the oil price is only going one way in a 20 to 30 year average?
Well, it depends upon how much oil capacity you really think we have for relatively easy oil. I mean, you make the assumption that we've found all the easy oil. Let's say suppose we have a relatively massive amount of oil that can be developed at $50 or less. What's going to stop people from developing that oil? Unconventional oils, most people don't think that that's the case. Most people think that as we continue along in unconventionals, that level is going to have to increase, what the price, but we're producing unconventionals at lower prices than we did before. The prices for large discoveries in Brazil, the prices for developments in Middle East and Russia are all under those numbers. So a lot of this is going to be dictated by oil demand. We're a little jaded now because oil demand had been for many years growing 1 million barrels a day every year. Sometimes a little more than 1 million barrels a day. And so if it was 1 million in 2000, it's going to be 110 in 2010. It's going to be, 120 million in 2020. And so under that scenario, if you look at it and look at the kind of pre-existing declines, you think, wow, we have to add, a Saudi Arabia every, 5-10 years worth of oil in terms of barrels per day. But it's not in the flat demand case. It's hard to say what that clearing price is going to be. And part of it's going to be dictated by the prices on the renewables. Remember, the natural gas prices, natural gas is one of its primary uses is for electric power generation. Now, coal prices have gone to extremely low levels, and in many cases, well below the cost of extraction. because natural gas is a much cheaper alternative. Well, to the extent that renewables and become cheaper, whether by government subsidy or by advances in technology, and it's been both, that essentially is going to put an upper limit on what natural gas prices can be, because people will accelerate capital investment into those. Now, there is probably a limit on how much of a very large country's electric power can come from renewables. People have argued, because of reliability and storage and a couple other things, people have argued that numbers like 20 and 25%, and there's some technical issues associated with the actual electric power generation from thermal generation units. As it turns out, every time if I flip off the lights, then somewhere in the system, somebody starts generating a little bit of electricity, but it balances very closely supply and demand in terms of generation. And it's much harder to do that with electricity from solar and wind. So you need a fair amount of it, but technically that percentage that can be from renewables keeps going up. And there are some estimates now that suggest it could be a very large fraction.
Thank you, Nathan. It sounds like technology is going to be a very large uncertainty in the outlook, the energy mix. We have another question here. Thank you for your insight, Nathan. If you owned an oil and gas company today, would you repurpose or shut down or do nothing in light of your future views?
Well, clearly, if I owned an oil and gas company today, we're going to assume that I've been very careful with my money and I still have some good money, some money available. I would be out buying other operators. To be honest with you, there are some bargains out there. There are some people. There's a lot of money to be made in the oil and gas industry. We're over the course of my remaining lifetime and my children's. Two of my children are in the oil and gas industry. One is a son-in-law is a driller for one of the largest international E&P companies, and the other one is a geologist who is a recent alumni of a large independent and looking to find the next team he's going to join. So but this kind of generation, that's their profession, I still think there are opportunities for oil and gas. Now, I'm advising a lot of clients who want to do things, find a way to differentiate their oil and gas production so that they can be cleaner. I have a client today that actually raises money effectively because they can sell themselves as having a much lower carbon intensity than other oil and gas operators. So that quantifying how clean you are, and, eliminating flaring and eliminating pneumatic actuators in the field, that for production specialists, these actuators that open and close valves are powered by a little bit of gas pressure. They tend to release a little bit of methane every time they work, but you can use electric actuators that don't do that. You have ways to monitor methane emissions. I would have all that going, and I would wind up trying to make my oil company differentially cleaner. So that's what I would do, right or wrong.
We've got a question from YouTube, actually. So here we go. What are your thoughts on how we can reduce reliance on coal? Is it just making gas even more competitive?
Well, I didn't talk about the issue of carbon prices and carbon taxes, and I'm reluctant to do that. There are carbon prices or taxes in probably more than 50 countries and locales around the world. And they're complicated, and they range from truly trivial numbers to very substantial ones. The number one thing that would displace coal would be carbon tax. And that would allow people to make natural gas even more competitive in those areas. The regulatory bodies are going to have to use carrots and sticks. The problem is the biggest sources, the biggest coal usage is India and China. India doesn't feel like they need to be penalized and pay a disproportionate cost because they're not the ones who put the vast majority of the anthropomorphic greenhouse gas emissions into the atmosphere. And there's certainly a point to that. However, I took a train from Calcutta to Dhanbad, I think it's Dhanbad is where ISM, well, it got a new name there, but what was the Indian School of Mines. And it is through the heart of coal country in India. And they burn not coke, which we use in industry. If you don't know what coke is, imagine wood is to charcoal as coal is to coke. That gives you enough to think about it. They're not burning coke for industry. They're burning raw coal. And the kind of coal they get in most of India is dirt mixed with coal. It's a very poor quality coal. And so it's just dark gray, the whole train ride. Very polluted, very, very serious problems. China still has a huge amount of coal production, and almost every forecast for China is not that the coal is going to go down, is that it's going to go flat and all the growth is coming from something else. So if instead of tariffs on Chinese products because President Trump doesn't like what China is doing, if there were tariffs on Chinese products that were strictly tied to the carbon intensity of their manufacturing process, that might drive Chinese manufacturers to away from coal. But because coal is cheap, because coal is a domestic energy source, because China imports so much of their oil and natural gas, very hard to see them radically changing that. They have certainly moved a lot of the coal-based power and plants away from the largest cities, though. So the impact on Shanghai and Beijing is decreased. But I think that there's going to be a need for a kind of a regulatory alternative of some type, whether it's pricing or taxes, tax breaks, probably carrot and stick, if you know that phrase. Yep. I never know where I'm using some Americanism here, but I hope carrot and stick makes sense. Okay. Yeah.
So your answer leads quite nicely into the next question here, which goes along the lines of the investment required for CO2 sequestration seems to make it cost prohibitive, especially when it is the developing world that will be growing demand, trying to get a similar standard of living that we have in the developed world. How do you convince the developing world to make the additional investment?
Right. Well, if you look at the countries that are generating the largest CO2 emissions, and that are certainly the countries that are most dedicated to and should be the most dedicated to reductions, you're talking about China, India, the EU, and the US. So this is the big guys. And for shorthand, I was including the UK and the EU. Sorry about that. I realize that's a sort of recent breakup, but so the UK as well. And what we need to do, if the intelligent thing is to go after the worst CO2 emitters on the planet first, the highest CO2 emissions in absolute volumes, the highest purity CO2 emissions. We're seeing some activity in northern Germany, for example, that is straining at a gnat in terms of what it's going to do in terms of the world's CO2. I mean, there's no possible way that makes any sense. And it's very expensive. Whereas in India, there are coal to natural gas plants who emit, and that chemical process emits an enormous amount of almost pure CO2. And it's just vented to the atmosphere. I mean, just vented. If the German government was really interested in reducing CO2 emissions. For a tiny fraction of the price they're going to spend on some of the activities they're doing now, they could go just voluntarily put in a carbon capture and storage and pay for all the costs of identifying the reservoirs and storing that carbon, sequestering that carbon, and would make a much bigger impact on the planet. We need to be focusing on what will really work. And there are lots of things that will work better than others. Right now, there's this argument, should we do blue hydrogen or green hydrogen? And I'm a big fan of hydrogen. But if you want to clean up hydrogen, the biggest impact you can do is go to the US Gulf Coast, where most of the hydrogen is manufactured for refining and processing, and clean up the gray hydrogen that's being produced today. And there's gray hydrogen being produced in essentially every petrochemical plant and refinery around the country. Let's go after those. Let's go after the beer plants, the cement plants, the iron and steel plants, the places that there are high point sources of CO2. And let's go after those first and get that carbon emissions down. So these countries that want to do that now, clearly, Vietnam still has a fair amount of coal. They are going to be very difficult for that government to spend the kind of money to do the cleanup that in the very short term that is needed. And Vietnam is, by comparison, a financially successful country. If you move over to Myanmar, whose economics are much, their GDP is much lower, or you go to, Bangladesh, which have a lot of people and much lower GDP per capita. That's not the place to start. The place to start is applying to people who want to make a difference and solve the biggest problems.
Thank you, Nathan. We've got a question, it's a fairly specific one. Goes along the lines of, compared to oil and gas production, what specific technologies do we require for carbon capture, utilization, and storage?
Good. Well, there are really quite a few. Carbon capture requires you to separate CO2 from flue gases associated with production. So if you look at the tailpipe of a big factory that burns a lot of natural gas or burns a lot of coal, what comes out of there is a combination of a little tiny bit of unburned methane, but CO2 that's generated in the processes, NOx's, which are generated in inefficient combustion associated with the process, and lots of other nitrogen and stuff that needs to just go back to the atmosphere. And so this is a fairly corrosive set of vapors at relatively low pressures. So it has to be compressed, it has to be treated, all the kinds of things that we know how to do in gas plants, petrochemical plants. And the CO2, with a couple of technologies, there are mold sieves, there are a variety of things, has to be concentrated to a point where it can then be compressed up to a pressure that's high enough that can be injected into a wellbore. Now, those wellbores look a lot like our conventional oil and gas wellheads and wellheads for a gas injection well. If there's any water vapor associated with that with CO2, that obviously generates a very corrosive liquid. So it either needs to be very well dehydrated, or it needs to be the kind of steels that, or plastics or other lined tubulars. Then that has to be injected into a reservoir that will accept it and keep it, or in the case of EOR, obviously displace oil, and parts of it are there. Some people have pumped these into partially depleted unconventional wells, let them soak and produce them back. A significant amount of the CO2 stays in place, and that can be recycled in a CO2 flood. a fraction of the CO2 is produced that's injected, and that tends to be recycled and back into the flood. But in many cases, we're trying to put that CO2 in permanently. And there's a lot of places you can do that. The best and easiest one is depleted oil and gas fields. And a depleted gas field is the ideal one. And of course, you have to look at the seals and do the geomechanics associated with this. Geomechanics is an extraordinarily important part of this, because you're not going to do this for fun. This is not, there's no, nobody at Exxon or Chevron or Total, no matter how well-intentioned they are thinking that, carbon capture and storage is a recreational activity. They're going to do it because they, get lower taxes, or they get, carbon price, they can sell it, something that is going to pay it. But if I'm a taxing authority, I'm not going to, give Total the money or decrease their taxes until I can get some proof that it's going to stay there. And so there are other things that we need to do as petroleum engineers that are specific technologies associated with monitoring. So we need to monitor the wells that access it. We need to do various monitoring activities to make sure that there is no migration. Obviously, the pressures can't go in and exceed the initial part. Now, another part of CO2 injection storage is into marine aquifers. So offshore into a super high permeable, super thick, laterally very extensive water bearing interval, you can put those CO2 into those. Those reservoirs are undersaturated with respect to CO2. However, there is a higher injection pressure required than injecting into a depleted gas field. There's already something in the pores that you have to physically displace. And there is a kind of a limit and you've got to both model and monitor that plume. So there's reservoir monitoring associated with this. There's modeling. And these are all the kind of stuff that petroleum engineers know exactly how to do.
Thank you, Nathan. We've got an interesting question here. Do you think the government, educational system, and international bodies should limit prospective students' interest in the oil and gas related courses owing to the challenges that oil and gas companies face in recruiting new intake?
Well, no. Let me go ahead and answer it. And let me say why. That interest level is self-limiting. Okay. It's self-limiting associated with employment opportunities. It's self-limiting associated with how successful various programs are around the world. There's no need for that as a government regulation. If you look at the places where the government actually regulates the number of students who can take something, there are some countries that do that, and they just, there are countries that just say, okay, we're going to have so many doctors, so many lawyers, so many engineers, so many scientists, and they compete to get into the best spots. They're highly competitive from a relatively early age, and most of Europe and the U.S. are not like that. People get to choose more or less what they want to do, and if you want to go to, Oxford and study the classics, if you're intelligent enough, then you can go do that, regardless of whether you are likely to get a job or just become Oscar Wilde. And the reality is we have those self-limitings. Now, the United States does have a de facto self-limiting thing on doctors and a much more efficient one on veterinarians. There are a lot more people who want to be doctors and who are capable and qualified to get into medical school than there are seats in medical schools. And certainly so for veterinarians. There is no limit on law schools and lawyers. Maybe that should have been reversed at some point. But I don't think that if you look even at the most negative thing, that I don't know what discipline would be something the government wanted to limit. But the self-limiting has really worked. Textile engineering as a discipline more or less has disappeared in the world. Okay, there's one school left in the United States that teaches textile engineering. No government action was required. The lack of jobs and employment pretty well took care of it on its own.
Thank you. I'm curious as to what you think about kind of the level of bankruptcies in the US unconventionals, and where are we headed with respect to that?
Well, it's going along at a very healthy clip, both for oil companies and for service companies. And for those of you who may not be as familiar with US bankruptcies, there's several different kinds. And unfortunately, there's a kind that many of these operators are going under, in which essentially the value of the equity, their stock, goes away. And all of their debt owners, from whatever sources, might get so many cents on the dollars. But they have an opportunity to raise some additional capital, and the debt owners and the providers of that new additional capital become the new equity owners. And this company has a clean balance sheet, basically. They don't owe, they had $5 million worth of assets and they owed 10. Well, now they owe 0. And they owe another 5. Well, all of a sudden, the employees are out there trying to drill, or in the case of service companies that survive this process, they are now competing even more vigorously for jobs at ever lower prices. So there will need to be, and this is my opinion, fortunately, I don't have to apologize for it. It's also the opinion of my company, which is me and a couple of friends. We're going to need some serious consolidation in the unconventionals in North America. We have way too many CEOs of oil companies in North America. We have way too many chief reservoir engineers and far too many drilling engineers, sadly. CFOs and so forth. So we could do the same amount, and in fact, that we did at the peak with far fewer companies. And we're going to see the most efficient of those companies consolidate and buy up the acreage that they can do the best job with. And that we'll see the less efficient companies go away and disappear, even if quite a few of them survive various rounds of bankruptcy. And so I'm hoping that this bankruptcy thing abates, but the rate is not slowing down very much. It doesn't look like activity levels at $40 a barrel are going to increase. Marcellus and other gas things are probably going to need a number that's closer to $3 just to be at a break even, and natural gas in North America is less than $2. There are still a couple hundred rigs in the U.S. running after unconventionals, and the very best of those wells are clearly economic at below $40. So the very best wells being drilled are very, very economic. But the in aggregate activity of operators is probably going to require at least 50 before you saw that these companies are generating enough money to avoid bankruptcy.
The 50 is the magic number then, is it? Okay, we'll take one last question, Nathan, and then we'll call it. Will the energy transition result in oil being used solely for chemical feedstock and no longer for transport, and hence oil demand reducing very sharply?
Okay, well, great question. Almost all the forecasts, if you go in and dig into them and see the transportation forecast, everybody has a transportation forecast that's declining. I had a chance to go to, I've been to more Saudi Aramco research facilities than most people at Saudi Aramco. I made, as SB president, I got a chance to do that, whether it was China, MIT, the UK, and the Kingdom. And when I went to the one in Detroit, which is most people are surprised that Saudi Aramco has a research facility in Detroit, they are working very hard to find ways that internal combustion engines can become more efficient, because the longer and more efficient, the more efficient an internal combustion engine is, and the higher miles per gallon that you get there, the longer that they stay competitive, and the higher the percentage of the total market. Now, Tesla, Elon Musk being a gazillionaire notwithstanding, there are still some significant challenges before we just turn over all to be electric cars. One of the most important ones is the electric power grid itself, and how much electricity we're going to be able to deliver to those. If you were to take, California has a goal of 50% zero emission vehicles by 2030 and 100% by 2050. To do that, you would have to double and quadruple the California electric power grid, respectively. And the fact is, California is unable at the moment to grow its power grid to the current demand levels. So we may need some hydrogen as a serious transportation fuel. So I think natural gas, coupled with carbon capture and storage for hydrogen, can play a role in zero emission fuels. But as far as liquid fuels for oil and gas, internal combustion engines, I think we'll see those decline over the course of decades. And if the forecasts are right, then oil will continue to be used for increasing amounts of petrochemical and refining and other higher value products, frankly, than transportation fuels. I do think that liquid hydrocarbons are going to play a role in air travel for decades and perhaps forever. It's far more efficient than some of the alternatives. There are alternatives that are being looked at, especially for smaller, imagine a drone that could carry a dozen people, imagine an electric helicopter. So yeah, not a lot of people are imagining an electric 747. So we're going to see liquid hydrocarbons in airplane wings, I think, for your careers. But fair question, and a good point. Our increased use of oil and natural gas for higher value than transportation and space heating is important.
Well, Dr. Nathan Meehan, thank you very much for this evening. And thank you everyone for joining us, and see you next time.
Cheers.